Alright, what's up guys? It's Probability by Pitman, Chapter 2, Section 5, Problem number 6. Alright, so in a hand of 13 cards drawn randomly from a pack of 52, find the chance of A, no court cards, which is a Jack, Queen, King, or Ace. Okay, seems easy enough. So we know that a hypergeometric would be the appropriate distribution to use in this situation because we're drawing 13, so we have 13 trials, right? 13 cards drawn. However, they're not independent, right? Because the result of, like, for example, the nth trial is dependent on the n minus 1th trial. For example, if you have one king left in the n minus first trial, and you draw that king here, then we know the nth trial cannot draw a king. So basically, all the trials are dependent on each other. You know, we're drawing without replacement. The result of one trial impacts the result of another trial. And because of that, a hypergeometric distribution would be the perfect choice. All right, so to go over what a hypergeometric distribution is, it is, here, let me draw it out real quick. It's pretty simple. We'll have G total good options. We want to pick little g of those good options. We have big B bad options. We want to pick little b of those bad options. And we have big N and little n, where big N is just big G plus big B, and little n is just little g plus small b. It's very simple, and if this is a little confusing, I think it'll be a lot more clear once I do the actual problem. So, in this situation, a good uh, a good individual is a card that is not a jack, queen, king, or ace. So, we have 52 total cards, which happens to be our big N. Of those cards, 16 are these face cards. We know this because there are 4 face cards, of which there's 1 in each suit. So 4 times 4, 16. If you didn't get that, that means like a king can be a heart, he can be a spade, he can be a club, he can be a diamond. There are 4 types of kings, and you can do the same for all 4 of the face cards. Okay, I hope that made sense. So if there are 16 bad cards, where bad is a face card, jack, queen, king, or ace, then we know there are 36 good cards because they are not a jack, queen, king, or an ace. So we'll call big G 36 because there are a total of 36 good cards. Of those 36 good cards, we want to draw 13 of them because we want to draw 13 cards. We want all of them to be of the good type. Then we have 16 bad cards in total, but we want to draw 0 of them. So big B is 16, little b is 0. All right, and we'll divide that all by big N, which is simply 52. And our little n is just the total of these, so it's just 13. Yeah, so that would be our answer for part A, the probability of no court cards. Okay, cool. I hope that made sense. So now part B. It's a little more interesting. At least one ace, but no other court cards. So let's do the same thing where we include ace as a good card. So that means we would remove 4 from the 16 because we would want our 4 aces to be included in the good subset of our deck. We still want to draw 13 of these cards, but now there are 12 bad cards. Since we're not including the ace card, we're including all the face cards except the ace. We want to draw 0 of them. And then the same idea, we total them. But this isn't the end of the story because this just means that ace can be drawn. It doesn't mean that at least one ace has to be drawn. So this probability includes drawing like 1, 2, 1, 1, 1, 2, 2, 2, 3, 3, 3, 3, then a 4. And you'll notice that, sure, we drew 13 cards that are not faces, but none of them are aces. We want to draw at least one ace. So we have to subtract the possibility of this happening. So we'll call this having no face cards drawn. So we'll say this is P of ace or actually let's just write P of 13 non jack, queen, or king. And we'll say now we want P of non ace, jack, queen, king. We want to remove the possibility of having non-face cards, which is what's happening here. So you'll notice that that's actually exactly what we calculated here. So all we have to do is subtract our answer from part A. So 36 choose 13, 16 choose 0, then 52 choose 13. Wow, that was pretty simple, wasn't it? And that's actually our answer. You can actually think of it, here's a better way to think of it. P of non Jack, Queen, King is equal to P of P of, sorry for that pause. There's a bit of a power outage going on right now. Okay, so probability of a non-Jack, Queen, or King is equal to non-Ace, Jack, Queen, King plus probability of at least one Ace and non-Jack, Queen, King. So we're adding together these two realities, right? So what we want is this. So we can just use some simple math to get P of, I'll just write it like that, greater than 1 ace, J, Q, is equal to, remember this is equal to that, P of J, Q, K minus P of A, J, Q, K. And these bars are equal to complement, so non-A, J, Q, K. And you'll see that's exactly what we did here. Probability of not getting a jack, queen, or king, so aces are allowed, minus the probability of not getting an ace, jack, queen, or king, which is what this is. All right, cool. I hope that made some sense. And I will do part C. At most one kind of court card. Okay, so at most one kind of court card means that you can have 0 court cards. You can have you can have 0 court cards, 1 to 4 of an ace, queen, king, or jack. Okay, seems easy enough. Let's write that out. So probability at most one kind of court card is equal to P of plus P of, so this means none of them, then this is just aces allowed. This is, sorry, okay, at most one kind of court card. Okay, yeah, no, okay, make sure, just had to make sure. Okay, so then this is um jacks allowed. This is kings allowed. And this is queens allowed. And then now we can just use the techniques we learned before. So probability of no ace, jack, queen, or king is exactly what we calculated in part A. So 36 choose 13. 16 choose 0, all over 52 choose 13. And then we can do the exact same process with the rest, right? So probability of A, jack, queen, king. So this is saying, think about this one is there can still be 0 aces. It just means at most one type is allowed. So I think in this situation, we don't really need to go with the fancy at least one technique we used before. We can just use a regular hypergeometric where we have 40 allowed, which we're allowed to draw 13. This 40 includes the aces. Then we have 16, or sorry, not 16, 12, 0, because we don't have, not including the aces in the face cards anymore. and then it's 5213 again. And then you'll notice that if we repeat this with the rest of the face cards, it's the exact same thing. So rather than write it all out, I'm just gonna write times 4 because we're just adding the same thing 4 times. All right, cool. And that should be our answer.
Alright, cool. Thanks for watching, and I hope that was at least a little helpful.